Oh. Hello and welcome back to Calculus 3. Oh, no, Calculus 1. I just talked about Calculus 3, so now Calculus... Hello and welcome back to Calculus 1, section 4.3. There we go. See, when you reset, everything works fine. First and second derivative test. The book has a silly title, what derivative tells us, or whatever it is. But the focus of this section is to learn about increasing, decreasing, min-max again, and concavity. So I'm going to show all of those on a single graph, and then we're going to break that down into parts and take care of everything one by one. But I want to talk about all of them in one shot first. For that, this is all I need to draw. Is some function f of x. We are going to identify max, I don't care, absolute or local, and min. And now I am going to use blue. Oh, I forgot to put x-axis. Oops. There is x-axis over here. So now in blue I have this interval over here on which the function is increasing. And then I have another interval over here on which function is increasing. And in red I have a portion on which the function is decreasing. Please note that I am using intervals on x-axis. I'm not using points. I'm using intervals, so x1, x2. Intervals on x-axis to describe the intervals on which the function is increasing or decreasing. We want to know that because you invest the money and you look at the graph, right? If the graph is going up, you're making money. If the graph is going down, you're losing money. Pull it out, right? So we want to know the concepts of increasing and decreasing function. Now, there is another concept that we worry about, and that concept, I can do it, actually green is the bad color for that. Maybe orange, huh? Somewhere over here, the orange is terrible too. How about the highlighter? Nothing that I do would actually make this good. Alright, so what should I use? You can't see any of these colors. The space, this one, right? Galaxy. Nah, a galaxy one. All right, fine. So now that point there, which is the galaxy point here, that's terrible. We are going to have a concept of concave down I am going to leave it just because, and then concave up. This was a terrible idea. But there you go. All right, fine. Now I'm just going to put this back to orange, you know. There we go, perfect. Guys, these are the concepts that we are going to observe. The galaxy point I put here is going to be called eventually inflection point, and that point will separate parts that are concave down, which spills the water, and concave up, that holds the water, like cups. And then you also have the blue and red concepts of increasing and decreasing function. Then you have the critical points, which are actually now including the new galaxy point. min-max, and inflection point. So those are all of the concepts that are in this lecture, all of it. So what do we have? Well, the first derivative test is going to give us increase, decrease, min, and max. First derivative test. Theorem. Let f be differentiable on some interval a, b. So now we have number one, if the first derivative calculated at value c, oh, I forgot to say, and c is element of a, b, so it's somewhere in this interval. So if f prime of c is less than 0, then f of x is decreasing. Number two, if f prime of c is larger than 0, then f of x is increasing. We learned this in chapter 3 when we drew the derivative off of the function. And number 3, if f prime of c is equal to 0, that's critical point, which is min or a max. That's it. Obviously, we're going to practice this on the cheapest functions we can find to learn the procedure. So if I have that f of x is equal to x squared, now we already know what that looks like. We know that this part is decreasing, this part is increasing, right? We know this stuff. But let's calculate it. So what do I need to do? Well, first off, I see that my interval AB here is negative infinity to positive infinity. It's the entire domain of x squared. So the derivative is 2x. We set that equal to 0 to find critical points. So x equals 0. Now, what do? I partition the domain using critical numbers. I'll write that here as a rule. We partition the domain using critical numbers and vertical asymptotes. So this is what we do. Now we only had no vertical asymptotes for x squared, and we only have one critical number, which is 0. So now, when we do the partitioning, pick test points C, 1 in each region. So pick partition. I'm going to pick -1 and +1 because it's cheap, it's easy. And now, first derivative test, f dt, is compute the first derivative at -1. Well, the first derivative was 2x, so 2 times -1 is -2. That's less than 0, implying f is decreasing. And then for the derivative at +1, you have 2 times 1, which is 2, which is larger than 0, which says that f is increasing. So we have a decreasing here and increasing there. Do you all see what I've done? I went back to the graph and I said for -1 test point, I have decrease. So on that partition, I have decrease. On the other one, I have increase. What do you get for free from this information? So we found the critical number, we did the partition, we picked test points. You can pick anything. If you like pain, pick e to the pi, it's fine, right? And then we calculated, we ran the theorem we just had, right? Calculating our test points in the first derivative. It's called first derivative test, so you're plugging into the first derivative. And we got less than 0, which means decreasing, right? So we put the decreasing arrow for -infinity to 0, we put the increasing arrow for 0 to positive infinity. All of that stuff was calculated. What did we get for free? Other than the cookies, thank you very much.
Do we get that the minimum point
Yeah.
is between 1 and -1?
You get that you have a minimum point at 0, 0 for free. Because look, decrease, increase, right? You fall, you hit the rock bottom, you bounce up. The rock bottom was your minimum, right? So, from this calculation that you work for, you get the information on what your critical points are for free, which is awesome. No additional work required. You remember the calculation we did with 1.1 and then we had to think, right, whether it's min or max? None of that stuff is necessary because now you get it for free. So, that's a minimum, and we get that for free. Yay. So now, what's the answer? Right? What do you write down for those 2 points? Right, you have your 8 points of partial credit work, and now the 2 points for the correct answer. What do you write? You write f of x is decreasing on -infinity to 0. F of x is increasing on 0 to infinity. 0, 0, minimum. This is your answer. So this is the answer that you must present at the end of the problem. What?
Sounds like Russian attack.
Hello? Misho. Yes, it's still. That was it. All right. Try to. I'll be right back. Try to work this thing for. Next example. F of x equals 1 over x. I'll be back in 19 seconds. So we have no critical points, right? But we do have a vertical asymptote. So we still get to partition at 0. And pick 2 test points. So those are your C's. And now we do our first derivative test, FDT. F prime at -1 is -1 over -1 squared, which is -1 less than 0. Function is decreasing. Boom, arrow decreasing. Now, F prime at 1 is -1 over 1 squared, which is also -1 less than 0. Function is decreasing. Do we all see that? Beautiful, right? We also see there's no min or max, no critical points. We have a partition for vertical asymptote, giving us 2 different regions. -infinity to 0 is the one region with a test point of -1. Then we test -1. And we got decrease because it was less than 0. And then 0 to infinity is the second region. We pick test point C. We plug in test point C, we get less than 0, another decrease. On our diagram, we have a decrease followed by a decrease. Well, clearly that cannot be min or a max. Also, we know that we partitioned on the vertical asymptote. And having the vertical asymptote means that we have we cannot have a point along the vertical asymptote to be a min or a max to begin with. So, yeah. The problem is solved. Now I need to write the answer. Right? So I will say f of x is decreasing on -infinity to 0 union 0 to infinity. So we are uniting the 2 sets, and we have no min max. Done. So f of x is decreasing, and there is no min max value. So the first one was partitioned on the critical number, 0. Second one was partitioned on the vertical asymptote. Can you have both of those at the same time? Sure. Can you have neither? Yeah. Linear line has no min, no max, so no critical points. And it also has no vertical asymptotes. So you can have functions that have neither.
So you have to do a test point in each quadrant that the function passes through?
Yes. Each region, yeah. So I want to go and find a problem. So something that it's not too crazy. For instance, something that would be, you know, nice and pleasant to compute. For instance, 32, square root of 2 sine x minus x. Yes. I know how much you love trig. So f of x is given as square root of 2 sine x minus x on interval 0 to 2 pi. Well, I know that this has no vertical asymptotes, so there will be no partitioning there, but it might have critical points. I have to go, take the derivative, see what happens. So this is a square root of cosine x minus 1. And I set this equal to 0 so that we can compute stuff. So now from there, cosine x is equal to 1/2. Sorry. Cosine x is equal to 1 over root 2, which is when you rationalize root 2 over 2. Now, on the unit circle, all students take calculus. Cosine is positive in a first quadrant and the fourth quadrant, so these are our answers. We're looking for x equals pi over 4. And x equals 7 pi over 4. I know that inverse cosine of root 2 over 2 is pi over 4, because cosine of pi over 4 is root 2 over 2, which is in the 45 degree. That's what the pi over 4 is. Pi over 4 radians is the same as 45 degrees if you use degrees. So this is what I have. And now I have, perfect. So now what I have is the partitioning, right? So now note that my endpoints are 0 and 2 pi, because the domain was chopped up for us, right?
Is that a 7 next to the pi over there?
7 pi over 4, yeah. So I partition at pi over 4 and at 7 pi over 4. And then we have the endpoints here. Now the nice value to pick in the middle is pi. That's the cheap one, clearly, right? And now I need to pick 2 points in between. So pi over 8 and over here 15 pi over 8 as test points. How did I come up with 15 pi over 8? Well, I know that I need over 8 because I am in between quarters and whole number, right? So pi over 8 would be in the middle. Now 2 pi is 16 pi over 8. So 1 less must be 15 pi over 8 if you go 1 less. That's how I know to pick 15 pi over 8. And now we have to do first derivative test. So we are testing the 3 red points. We have the first derivative computed at pi over 8. First derivative is square root of 2 cosine of pi over 8 minus 1. That's where the abacus, right, comes in. you make sure that your calculations are in radians. There we go. And now we say square root of 2, close parenthesis, cosine of pi over 8 and then everything minus 1 will give me, I don't really need to know the exact value, I just need to know whether it's larger or smaller than 0. So this is about 0.3. That's bigger than 0. I have an increase on this piece. Now f prime calculated at pi is root 2 cosine pi minus 1. Cosine of pi is negative 1, so I have root 2 minus times negative 1 minus 1, which is further equal to negative root 2 minus 1. I don't care what this is. I see it's less than 0, so it's going to be decrease. And finally, we have f prime computed at 15 pi over 8, which would give us the same 0.3, which is larger than 0, so we have another increase. So what do we get for free? We get a lot of stuff for free here. We know that there's a max at pi over 4 and a min at 7 pi over 4, and that's a big deal. Now you can go back to original equation and calculate their y values if you want to. Answer. F of x is increasing on 0 to pi over 4 union 7 pi over 4 to 2 pi. F of x is decreasing on pi over 4 to 7 pi over 4, which is the gap in the middle. Then we have maximum at x equals pi over 4, and we have a minimum. You can go calculate y values. X equals 7 pi over 4. Get y values. There we go. So this is your answer. The final 2 points, right, on your exam. Right there. To make sure you understand, right, the function is increasing. On the graph it will be going up to the right, decreasing, goes down to the right, and then increasing again, so. This is first derivative test. It's a very structured procedure. Very structured procedure. Step number 1, take the derivative, calculate critical points. Step number 2, collect your critical point numbers and your vertical asymptotes, partition the domain. If the domain is restricted, you only partition that part of the domain. Pick in each of the regions, pick a test point, and then run through the calculations with those test points to satisfy our theorem from the top, which says your test point is to be plugged into first derivative. If it's less than 0, you have decrease on the function. If it's more than 0, you have increase on the function. If it's equal to 0, well, it's critical point. Oh no, we have a second derivative test. I was about to do the marker drop, but then I realized we only did half. Now, second derivative test. second derivative test is about concavity. We can also use concavity to come up with the min and max for free. X squared is concave up. It has min or max? Min. So x squared is concave up, right? It has a minimum. Negative x squared is concave down. It has a max, right? So concave up has a min, concave down has a max. That should be common sense just when you look at them, right? Concave up has a minimum, concave down has a maximum. So you get min max again for free. You might be wondering, well, why? Why would we do the second derivative test? Do we actually gain anything from it other than the headaches in calculation? Well, to immediately answer that question, let's take a look at some money portfolios. This is another thing that I always do when I teach these concepts. So I'm going to put 3 graphs over here. All of those graphs have the same elapsed time. All of these graphs are for money. So your y-axis is money. And they all invest the same amount to begin with, which is, say, 10K. I think that's the minimum that you have to invest for certain things. So here we go. These are the 3 graphs. And now I want to ask you, as the time passes, which portfolio or portfolios made money? In time. And the answer is?
All of them.
All of them. Exactly. All of them. So are all of these increasing graphs? They are. Because over time, they all generated extra money. Right? Now, here is a $10,000. Which one do you invest in? Number 1, number 2, number 3. And obviously, if you care to explain why? So, do you invest in number 1, 2, or 3? If I give you 10K, where do you put that money?
1.
So you said 1, you said 3. Anyone else? You're allowed to change if you want to. Do we have any business people over here? No business people? It's all biology and physics. You don't care about money? Necessary evil? Which? So great. So we either invest in 1, 2, or 3. Good. Because that's what I got. 1 or 3, and then or 2 later on. So great. Yeah, it's definitely one of them. One of these is the right answer. The other 2 are wrong answer.
So one you go up really quick and you level out for the
So over the long period of time, is that something you want to have? No. So we eliminate number 1.
Well, what if you just... it goes up fastest, so then you can reinvest the money in something else,
It just resets because it's a term. You don't get to move the money mid-term and pick up different. So we want to invest in number 2. Number 2 is the exponential growth. Number 1 is logarithmic or square root growth. Those are slow. And number 3 is linear growth. We all know that exponential growth is the boss. So we want to invest in the exponential growth, which is the second graph. Do we all see that's the only one that is concave up?
Mm-hmm.
the top is concave down, and the third one is concavity is 0. There is no concavity. It doesn't bend up, doesn't bend down to hold or spill water, right? So you have a concave down, concave up, and concavity is 0 on the third graph. You do want to invest in number 2. So this is where concavity comes in, right? To go beyond the first derivative and give us the fastest way to change the change. Ooh, too many words, huh? Think about it. The first derivative is change of money in time. The second derivative is how fast you change that. So you can change. Maybe I can explain it also through velocity, acceleration, and so on. For you to cover the distance from, let's say, from RVCC to your home, you have to have a velocity change from 0 to something, and that's acceleration. That's the second derivative, and that's actually concavity. You have a positive concavity there, right, to change it quickly, or you have a negative concavity so you can annoy everyone behind you. Right?
Are derivatives in calculus related to a derivative, which is a financial product, at all?
The derivative in business is called the marginal. So marginal cost, marginal
There's a
profit.
financial product called derivative product of a commodity. Does it have anything to do with it?
No. That's probably why they call this marginal. So now, let's talk about second derivative test. And guess what? Second derivative test is absolute mirror copy of the first derivative test, except you're doing it on a second derivative. You do everything the same. Find the second derivative equally to 0. Get the inflection points now, not critical. Get the inflection points, partition over inflection points and vertical asymptotes. Pick the region, pick the points in each region. Run the second derivative test. And then just say concave up, concave down, concave up, and then min, max, 3. So those are the things. Let's go. I have the theorem now. Let f have second derivative. That means you are able to differentiate f twice. And C element of AB, right? That's our thing. So what do I have now? I have number 1. If the second derivative computed at the test point C is less than 0, then f of x is concave down. Number 2, if f second derivative of c is larger than 0, it's the second derivative, I'm not sure if you picked it up, then f of x is concave up. Number 3, if f double prime of c is equal to 0, f of c is an inflection point. Now I just want to write one more sentence about the inflection point. Inflection point is where the concavity changes. So concavity changes at inflection point, from up to down or down to up. Concavity changes. So concavity changes at the inflection point. Just like your increase-decrease change at min and max, right? You are going increase, then you reach a maximum, and then you go decrease. So maximum changed, increase to decrease. Does that make sense? For the decrease, you hit the minimum and then it changes to increase. So min and max change, increase and decrease. Inflection points change concavity. Calculations for this are, as I said before, identical. Same steps. So second derivative test. Let's do a vanilla problem first. So say we take x cubed minus 3x squared. So f of x is x cubed minus 3x squared. This is problem 77 in the new textbook. Third edition textbook. So what do I have over here? Well, I have the first derivative, f prime, because I need that to get to the second derivative, is 3x squared minus 6x. And now the second derivative, which is what I need to do the second derivative test, is going to be 6x minus 6. We set this equal to 0 to find inflection points. That's our job. And from here, we come up that x is equal to 1. So now, f of 1, well, we don't need the y value for it, but so this is inflection point number, just x coordinate. So now, again, here it is on side in blood. We partition over inflection numbers and vertical asymptotes.
Where did you get x?
When I solve this equation, right? Move 6 to the other side, divide both sides by 6, x equals 1. We partition over inflection numbers and vertical asymptotes. Now we only have one inflection point and no vertical asymptotes. We are on the domain negative infinity to positive infinity, and we are partitioning at 1. Test points, well, clearly a 0 and a 2 because we're cheap. Second derivative test, s dt. We take second derivative and we plug in 0 in it to get 6 times 0 minus 6, which is negative 6, which is less than 0, which is concave down. So CD. F double prime at 2 is going to be 6 times 2 minus 6, which is 6, which is larger than 0, which is concave up. Answer? Remember, you need to have answer at the end. So we say f of x is concave up, or concave down, sorry, first. Concave down on negative infinity to 1. F of x is concave up on 1 to positive infinity. We did not compute critical numbers. We could, because we do have a first derivative. And then we could find out critical points. If you have critical points, those are min and max, and we can just look at the concavity and say which one is which. But at this point, you already know which one is which because you did the first derivative test before you did the second derivative test in the same problem. Now, many of you wonder, wow, these problems get to be very long. Do we actually get on a test a problem which says find the first and second derivative test for this function? And the answer is not quite. You actually get that problem in two separate problems. So there is a separate problem with its function for the first derivative, and then a completely different problem with a different function, right, on a different page of the exam, which has second derivative test. you have to understand that the procedure, and I hope you see that the procedure to calculate these things is the same between first and second derivative test. Concepts are changed, right? What you get from the first and what you get from the second. But, you know, if you are to print these two, put them side by side, I mean, they're identical. So I'll let you try one of the second derivative tests. By now, you should be masters of the procedure, at least. Let's go with problem 85, because this one has x squared e to the negative x. So try that. I just hope you did the product rule. If that is wrong, everything else is gone. Let's take a look at this together. So the first derivative will be the product rule. I say copy the first, the derivative of the second, plus copy the second times derivative of the first. Now, I'm going to rewrite this. I am not going to factor anything because that will create even more product rules. So this is going to be simply, I can put 2x e to the negative x first, and then minus x squared e to the negative x. Because now I have to do second derivative, and I have to do this again, right? Two product rules now. If you factor this, you have a triple, right, product rule. Or no, you have still a product rule. Yeah, still. No, you got a triple product rule because it's x e to the negative x and then triple product rule, yeah. So copy the first, 2x times derivative of the second, negative x e to the negative x, plus copy the second e to the negative x times derivative of the first is 2, minus, and then now the second product rule, copy the first times derivative of the second, plus copy the second times derivative of the first, which is 2x. So now what do I have? I have f double prime of x is equal to negative 2x e to the negative x plus 2e to the negative x. Minus and minus gives me plus x squared e to the negative x. And then minus 2x e to the negative x. These first and last term are the same, so we can add those. And then we see that we can kick out e to the negative x. That's common for all. And what's left inside is x squared minus 4x plus 2. Right? Minus 2. Minus 2x is minus 4x. Which is x squared and plus 2. Good. Yay! I have my derivative. It's a little bit of algebra, but nothing we can't handle. It's the weekend, obviously. We can do anything on the weekend. Everyone loves weekends. Or did we ruin that forever? So now we have e to the negative x equals 0. That one has no solution. And if there is no solution, that means no inflection point coming from there. X squared minus 4x plus 2 equal to 0. Might have a solution. We can crack the quadratic formula. So negative b, that's plus 4 plus minus 16 minus 4ab. That's 4, that's 8. Everything divided by 2. So this is 4 plus minus square root of 8 over 2. 8 is 4 times 2, so it's now 4 plus minus 2 root 2 over 2, which is 2 plus minus root 2. When I partition now, I go from negative infinity to 2 minus root 2 to 2 plus root 2 to positive infinity. So my partition is now these values. Now root 2 is about 1.4. So 2 minus 1.4 is about 0.6. So we can use 0 over here as a test point. We can use 2 in here because, as you can see, 2 minus root 2, 2 plus root 2, so 2 is right in the middle. And on the other side, we can use 4 because 2 plus 1.4 is about 3.4, so we can use 4. So these are the values that we get to use for our second derivative test. So now I have the f double prime at 0. That's e to the 0 times 0 squared minus 4 times 0 plus 2. E to the 0 is 1 times, in parentheses, everything dies except 2. 2 larger than 0, concave up. So we have concave up piece there. I compute for 2 and compute for 4. I told you what's going to happen. And you are welcome not to have it. Every time I go to a party, I say, oh, how's the cake? Terrible. Never going to do anything. Meanwhile, party. look at my calculation for 2. E to the negative 2 is 1 over e squared. That's a positive number. The parenthesis is negative 2. That's negative. Positive times negative is negative. I don't care what these values are. I just care if they're positive or negative. So, if you can cut out all the calculations, cut out all calculations. It's okay. So all I did is I made the argument at the end what's positive, what's negative, and then positive times negative is negative, less than 0, done. Yes, you can go take the calculator, figure out how much e to the negative 2 is, and then times that negative 2, you will see it's a negative number. But we really don't care what that negative number is. Now, we have a concave down. And for number 4, in this case, I know it should be concave up again. So, f double prime at 4 is e to the negative 4. We have 16 minus 16 plus 2, which is positive times positive, which is larger than 0, which is concave up. To finish this off, we write answer. And the answer is f of x is concave up on negative infinity to 2 minus root 2 union 2 plus root 2 to infinity. F of x is concave down on 2 minus root 2 comma 2 plus root 2, and we're done. That's our answer. The second derivative test is there for us to find concavity. Now, there is no reason for us to practice this anymore, because guess what next lecture is? Graphing functions by hand. And then the first and second derivative are part of those calculations. So by practicing that one, you will be practicing this anyway. So we don't have to practice this anymore. Bye. Now,